Hello, everyone. This is Yang Wang from Missouri University of Science and Technology. Today, I would like to discuss how we characterize the vertical transport of aerosols during deep convective events. Before we start, I would like to first acknowledge the help from my PhD student, Shinakia, who have been analyzing the dataset. I would also like to thank our collaborators, which include Dr. Dia Wang, Dr. Scott Giangrandi, and Dr. Jian Wang for providing their insights. I included a schematic diagram of our study, which shows the life cycle of aerosols during deep convection. And here we would like to focus on the convective downdraft of the aerosols from the free troposphere to the boundary layer, because we think that this convective downdraft may serve as an important source of aerosols in the boundary layer during pre-industrial conditions. The reason behind our hypothesis is that the boundary layer is generally a major source of aerosols in the atmosphere due to the new particle formation. And these particles, if they transport to the boundary layer, they can contribute to the CCM population and further affect the cloud formation. It has been a consensus in atmospheric science that these aerosols can transport from the free troposphere to the boundary layer through entrainment process, which is very prevalent and happens at all the time. But the entrainment process is generally a very slow process due to the slow entrainment rate. And the recent study by Jian Wang showed that over the Amazon forest, the deep convection may serve as a major source or an important source of aerosols, which transport these very small particles from the free troposphere to the boundary layer during a very short period of time. So we would like to figure out the relative importance of the entrainment and the deep convection as a source of aerosols into the boundary layer. Therefore, the goals of this ASR project include first, to gain a detailed and quantitative understanding of the aerosols transported by convective downdraft and their evolution in the atmosphere. And second, to examine the wet scavenging mechanisms and efficiencies of aerosols at altitudes or at different altitudes of the deep convection system based on aircraft measurements. And third is to evaluate the contribution of deep convection system to CCN as both a source and a sink of atmospheric aerosols, and also its seasonal variabilities. And in this poster presentation, I would like to focus on the objective one, which is to examine the prevalence of this vertical transport of aerosols at different geographical locations, and also to examine the correlation between the aerosol and deep convection properties. And in terms of the methods, we have been analyzing the dataset collected at the DOE ARM sites, which mainly include the Go Amazon campaign and the high-scale campaign. We also use the long-term measurement data at the SGP observatory. So we analyze the aerosol and trace gas properties, for example, the aerosol size distributions, the aerosol absorption, carbon monoxide, and sulfur dioxide. We also analyzed the cloud properties, for example, the cloud vertical distribution and the downward motion, which is provided by the Kaiser and the RWP. And because we're looking at the deep convection events, we also need to look into the meteorological properties. For example, the precipitation intensity, the equivalent potential temperature, or the theta E, and the solar radiation. So how does the aerosol look like during these deep convection events? So here I'm showing a case or an event that we're very interested in. So in the first panel, it shows the time series of theta E, which is the equivalent potential temperature, and the precipitation rate at during the Go Amazon campaign at the Ado site, which is the T0 site. And you can see that intense precipitation occurred during the local time of 2 to 3 a.m. And at the same time, the theta E decreased very significantly, which is an indicator of the deep convection event. So we further observed or further analyzed the concentration of the aerosols below 100 nanometer and the concentration of the aerosols above 100 nanometer, which you can treat them as the Aitken mode aerosols and accumulation mode aerosols. And you can see that when the precipitation or when the deep convection occurred, both concentrations decreased, which is because of the wet scavenging. But later on, the concentration of the atypical mode aerosols increased very significantly. And then they further dropped down because of the growth of these aerosols. And this is also reflected in the contour plot of the aerosol size distributions, where you can see there's an intense emergence of the aerosols with sizes of around 30 nanometer during the local time of around 2 to 230. And further, by combining the ground measurement data with the aircraft data, Jian Wang et al. Actually found that during in the Amazon forest, this deep convection mechanism can transport a large concentration of the aerosols into the boundary layer due to the convective downdraft. And the features of such event include intense precipitation, a rapid decrease of the theta E, the increase of the atypical mode aerosol concentration, and also the washout of the accumulation mode aerosols. So then we wonder, is this deep convection mechanism a prevalent mechanism for providing the aerosols into the boundary layer? The answer is yes. So we looked at the aerosol and cloud data during the high-scale campaign and also during the long-term measurement at the SGP site. Actually, here we found a very similar case during the high-scale campaign, where you can see that in the second panel, intense precipitation occurred during local time of around 8 to 10 p.m. And at the same time, the theta E decreased significantly. And during this time, you can see that in the aerosol size distribution, there's an intense emergence of the atypical mode aerosols and a substantial change of the atypical mode aerosol size. We further rule out the possibility of new particle formation because this event occurred overnight, and there's no significant increase of the sulfur dioxide concentration. But at the same time, there's a substantial decrease of the carbon monoxide concentration, which is due to the vertical transport of the air mass, because generally the carbon monoxide concentration in the boundary layer and in the free troposphere are very different. And because, or with the help of the cloud properties that's measured at the SGP site, we could really look at how the cloud developed during this deep convection event. And you can see that the cloud top height is above 10 kilometers, which is showing that this is indeed a deep convection event. So actually, during the 51 days of the high scale IOP periods, or at the IOP campaign, we found there are 8 similar events. And during the long-term measurement at the SGP Observatory in 2017, we identified 37 similar events. So with these data sets, we can look into the statistical correlations between the aerosol properties and the deep convection properties. So here in this scatter plot, we show the correlation between the change of the atypical mode aerosol size and the change of the theta E. Because if you recall the deep convection event, generally there's a substantial decrease of the atypical mode aerosol size, and at the same time, there's a substantial decrease of the theta E. So we found that there's a correlation or positive correlation between these two parameters, which is showing that these aerosols properties or the evolution of the aerosol properties is indeed caused by the deep convection. And this positive correlation is also reasonable because normally the deep convection events that has a more substantial change of the theta E means that the air mass is being transported from further higher up in the free troposphere, where the aerosols will generally have a smaller size due to the new particle formation. So in summary, we found that the vertical transport of aerosols during deep convection event is prevalent at different geographical locations. So the event is characterized with a rapid decrease of the theta E, an increase of the atypical mode aerosol concentration, and a decrease of the atypical mode aerosol sizes. So we also found that there's a positive correlation between the change of the atypical mode size and the change of the theta E. So in terms of the future work, we would like to correlate the downward mass flux that's observed by the RWP or the Kaiser with the aerosol properties to further understand the mechanism of the aerosol properties or the properties of the aerosols that's being transported by deep convection. So we would also like to examine the wet scavenging mechanisms of the aerosols and evaluate the impact of deep convection on season population in the boundary layer. So finally, I would like to thank our funding agencies. Thank you all for your attention, and feel free to let me know if you have any questions. Thank you.